Well, so in the previous lecture, we introduced the Jns Construction, which is a useful tool of constructing representations of C-star algebras out of positive functionals. This construction is indeed very important, and we will constantly use it today. So to begin with, let's recall the basic steps of this construction. So the initial data is as follows. We start with the C-star algebra. A is a C-star algebra. And little f is a positive functional, a positive linear functional on A. First of all, we define a pre-inner product on our algebra A by the following formula. So this is a pre-inner product on A. Well, this pre-inner product determines the seminorm the following way. In general, this is not a norm. This is only seminorm. So we look at the vector subspace and F on which this seminorm vanishes. And we have proved that this subspace can equivalently be defined as follows. This is the set of all elements A, such that f of BA is 0 for all B in our algebra. Or equivalently, this is the set of all elements A, such that f of A star B is 0 for all B. Now these equalities enable us to factorize the pre-inner product through the quotient of A modulo and F. And so this induces an inner product on the quotient by the following formula. So this is well defined, and this is an inner product on the quotient of A modulo and F. So the quotient becomes an inner product space, and we denote this space by HF0. Now, if we look again at this formula, this equality, so this equality implies that NF is not only a vector subspace, but it's also a left ideal of A. And so the quotient of A modulo NF becomes a left A module in a natural way. So we can consider the corresponding representation of A on H of 0. So we denote this representation by pi f0. Pi f0. So the respective operator, pi f0 of A, is just the left multiplication by A. So this operator acts by the following formula. Now, an important fact, which is not entirely obvious, but is true, is that this operator, pi of 0 A, is bounded. And moreover, its norm is less than or equal to the norm of A. So we can extend this operator, pi of 0 of A, to the completion of H of 0. So the completion is denoted by HF. This is our Hilbert space. And our operator extends by continuity to HF. And the extended operator is denoted by pi f of A. So we get a map pi f from A to the algebra of bounded operators, bounded linear operators on HF. And this is the Jns representation. This is the Jns representation of A associated to the functional f. Okay, let's now recall one more important property of Jns representations, which actually shows that they can be defined axiomatically. So let's denote by lambda f the map from A to HF given by the following formula. So it's just the composition of the quotient map with the inclusion map from H of 0 to its completion. And this map has the following three properties. First of all, the image of this map is dense in HF. Second, the inner product of any two elements in the image of this map, lambda FA and lambda FB, is given by the following formula. This is f of b star A. Actually, this is just the definition of our inner product. And finally, the Jns representation by f of A acts on each vector of the form lambda f of b as follows. Well, so these properties are immediate from the definition of our Jns representation. But it turns out that these map lambda together with the representation p determines this representation uniquely. In other words, we have proved that if we have a triple consisting of a Hilbert space H, a representation, star representation pi of A on H, and a linear map lambda from A to H, such that lambda satisfies these conditions, then it turns out that there is a unique unitary isomorphism of A modules between H and HF, such that the following diagram commutes.
Do we suppose that lambda is continuous?
We don't, but it will be automatically. This follows from the second property, actually. If we substitute A here, we see that the norm, the square of the norm of lambda A is f of A star A, but f is continuous. It's a positive function which is continuous, and this is estimated as the norm of A norm of f multiplied by the norm of A squared. So it will be continuous automatically. Okay, so there is a unique amodular isomorphism between H and HF such that this diagram is commutative. So this gives us an abstract characterization of Jns representations. Okay, so this was a brief summary of what Jns representations are. So today, our first goal will be to apply Jns representations to constructing the so-called universal representation of a C-star algebra. And by using this representation, we will prove the famous second Gelfand-Dimitrov theorem, which states that each C-star algebra is actually isomorphic to a C-star subalgebra of B of H for a suitable Hilbert space H. So we will discuss the universal representation. and the second Gelfand-Naimark theorem. Okay, so to begin with, let's recall some standard facts on summable families. So suppose that we have a normed space, say X. X is a normed space. An arbitrary set I, and a family xi of elements in X. So what we're going to do is to give a precise meaning to the following expression. So in general, the set I is not assumed to be countable and is not assumed to be ordered. So to give a precise meaning to this expression, we do the following. We consider the set the family of all finite subsets of I. We denote it by fin of I. This is the collection of all finite subsets of I. And we observe that this set is a directed, partially ordered set with respect to the inclusion. Clearly, it is directed because the union of two finite sets is finite. So now for each finite subset J of I, we denote by xj the following finite sum. So we take the sum of elements in our family over the finite set J. And we say, by definition, that our family xi is summable if the respective net consisting of such finite sums, xj, and indexed by finite subsets of I, converges in X. And if it converges, then the limit of this net is called the sum of our family. The sum of our family is the limit of this net. Okay, so this is the formal definition. But actually, it turns out that summable families, the notion of a summable family, can be reduced to the notion of an unconditionally convergent series. So this is useful exercise. So I claim that our family, xi, is summable to a certain element little x in our space if and only if the following two conditions are satisfied. Condition one is that xi vanishes for all but countably many indices. In other words, the set I0, which consists of all indices I for which xi is non-zero is at most countable. And condition 2 is as follows. If the set is finite, if I0 is finite, then the sum of xi over this set is x. So in this case, we have just the finite sum. And if it is infinite, but countable, then for each bijection phi from natural numbers to 0, the respective series sum over n x phi of n converges to x. So it's important that this property should be satisfied for each bijection. So in other words, summable families are essentially equivalent to unconditionally convergent series. That is, those series which converge independently on the order of the elements. So these two languages are equivalent, but in practice, it turns out that in many cases, the notion of a summable family is more convenient. For example, when we want to work with several families or with many families indexed by the same set, then it is not very convenient to introduce the respective support for each family, for each other family. And it's more convenient to work with summable families over the same index set. Okay, okay. Now let's introduce Hilbert direct sums of star representations. Hilbert direct sums. Well, first of all, let's call this a standard notion from functional analysis. Suppose that we have a family of Hilbert spaces, Hi. A family of Hilbert spaces. And let's denote by H the subset in their product which consists of those families Xi for which the following sum is finite. So we have the following simple exercise. First of all, I claim that H is not just a set, but is a vector subspace. Is a vector subspace in the product. And moreover, it's a Hilbert space. H is a Hilbert space. With respect to the inner product given by the following formula. So in particular, I claim that this last family is summable. It's a family of complex numbers, and it is summable. Well, the proof is more or less standard. In particular, the completeness of this Hilbert space is proved in exactly the same way as the completeness of the classical little L2 space. So this is a simple exercise for you. Okay, so we get Hilbert space, and the space is called the Hilbert direct sum of our family. The space is denoted, is called the Hilbert direct sum. Of our family. And it is denoted by the following symbol. So in order to distinguish between algebraic direct sums and Hilbert direct sums, I put the dot here over the direct sum sign. Okay, okay, let's now suppose that all these spaces Hi are star modules over the same Banach star algebra. In this case, we have the following simple result, proposition. Suppose that A is a Banach star algebra and Hi is a family of star modules over A. I claim that their Hilbert direct sum is also a star module over A with respect to the following action. So we apply our element coordinate-wise to each coordinate in our family. The proof is more or less straightforward. So the only thing I would like to recall is that each star representation of a Banach star algebra is automatically contractive. As if we have a star representation pi, then the norm of pi of A is less than or equal to the norm of A. In particular, this implies that for each I, we have the following inequality. Which implies that the above action of A on the Hilbert direct sum is indeed well defined. For each A in our algebra and for each X in the Hilbert direct sum. And more or less that's all. So the remaining part of the proof is automatic. So the axioms of star modules or star module are readily verified. Okay, and of course the same terminology applies to star representations. So we introduce the following notation. Suppose that we have a family of star representations by I of the same Banach star algebra A. Well, in this case, we know that each hi is a star module over A, so we can form their Hilbert direct sum. And the respective representation, the star representation of A associated to this module is called the Hilbert direct sum of our family of representations. The Hilbert direct sum of our family. And it is denoted as follows, by the same symbol of direct sum with a dot here. Okay, so now we are ready to introduce the universal representation of a C-star algebra. So suppose that A is a C-star algebra. We define its universal representation to be the Hilbert direct sum of all Jns representations pi f associated to states of our algebra. So the direct sum is taken over the family of all states of A, that is, of positive functionals of norm 1. And these representations will be denoted by omega A. Well, unfortunately, I don't have time to explain why universal representation is called universal. To understand this, we must learn some basic things on von Neumann algebras, and this will require several lectures. So we simply cannot afford this. But it turns out that indeed the universal representation has some universal property formulated in terms of von Neumann algebras and their normal morphisms. For our purposes, the universal representation is important because it enables us to prove the second Gelfand-Naimark theorem, which is one of the most fundamental results in the C-star algebra theory. So this theorem states that every C-star algebra has a faithful representation, a faithful or equivalently isometric star representation. So let's recall that each injective star homomorphism between C-star algebras is automatically isometric. So in particular, each faithful star representation of a C-star algebra is isometric. And specifically, it turns out that the universal representation omega A is faithful. To prove this result, we'll need the following important lemma. I claim that for each element A in our algebra, there exists a state f on A such that the following equality holds. The norm of pi f of A, where pi f is the respective GNS representation, is equal to the norm of A. Okay, so let's prove this lemma. First of all, we may assume from the very beginning that A is non-zero. Otherwise, there is nothing to prove. And let's recall that at the end of the previous lecture, we proved that for each normal element of A, there exists a state f such that f applied to this element, say if little a is a normal element, then there is a state f such that the absolute value of f of A equals the norm of A. So let's apply this result, but of course not to the element A, because here A is not assumed to be normal, but to the following element. So we find a state f on A such that f applied to A star squared is equal to the norm of A star squared. This is possible because A star squared is a normal element. Actually, it is self-adjoint. Okay. So I claim that this is exactly the state we're looking for. Well, indeed, let's apply the C star axiom, the C star identity, to the element A. So this implies that the norm of A to the power 4 is equal to the norm of A star A squared. This is just the C star identity. Then we apply the C star identity again, but now to the element A star A. And we see that this is the norm of A star A squared, because this element is self-adjoint. So by assumption, this is f applied to A. Oh, sorry. That's true, but this is true. But for my purposes, it is more convenient to interchange A and A star here. So I put the star here and here. So by assumption, this is f applied to A star squared. Okay, now let's recall the inner product on the Hilbert space of the Jns representation is determined by the functional f. And in particular, this number is nothing but the norm in the respective Hilbert space, or more exactly, the square of the norm of the following element, lambda f applied to A star. So this is the inner product of lambda f of A star by itself. Well, okay, let's now write this in the following form. This is pi f of A applied to lambda f of A star. Again, this is one of the properties. This is actually the definition of the Jns representation. So now we can estimate this as follows. This is less than or equal to the norm of the operator pi f of A. squared multiplied by the norm of lambda f of a squared, which is again the same as f of a star. And finally, since f is a state, we can estimate the second number here as the norm of a star a, the norm of a star, sorry, which is the same as the norm of a squared. This is because the norm of f is 1. Okay, and now if we look here and look here, and if we cancel the norm of a squared, what we get is that the norm of pi f of a is greater than or equal to the norm of a. This completes the proof of our lemma, because the opposite inequality is also true, and it is true for any star representation of a C-star algebra. Okay, now it's by using this lemma, it's easy to prove the second Gelfand-Dynamic theorem. So we want to show that omega a is faithful. Actually, we will prove that omega is isometric. And this is just a line. Namely, for each element a in our algebra, the norm of a is less than or equal to the supremum of pi f of a, where f runs over the set of states of a. This follows from the previous lemma. But if we now look at the definition of the universal representation, so the universal representation is this Hilbert direct sum, it's easy to see that the norm of omega applied to little a is just the supremum. It's just this exactly this supremum. So this is equal to the norm of omega of a, and the norm of omega of a is less than or equal to the norm of a, because this inequality holds for each star representation. And this completes the proof. So clearly, this chain of inequalities implies that omega is isometric. So we see that the universal representation is faithful. So it becomes, it is an isometric embedding of the algebra A into B of H, where H is a very big Hilbert space, namely the direct sum of HF over all states. So in general, this Hilbert space is very big. I don't claim that it is separable. Even if the algebra A is separable, the Hilbert space of the Jns representation usually is not separable. However, we have the following useful result, and this is an exercise for you. Suppose that A is a separable C-star algebra. Then, first of all, I claim that for each positive linear functional f on A, the representation space for the Jns representation is separable. This is very easy, because A, there is a continuous map from A onto the dense subspace of HF. But what is more interesting, there is a state f on A such that the respective Jns representation pi f is faithful. So we see that in this case there is no need to get an isometric representation of A. There is no need to take the direct sum of all Jns representations. It's enough to take only one of them, and it will be faithful. A hint is that the space of states is weak star separable in this case. So F is constructed from a weak star dense subset of C of A in a certain way. Okay. Our next goal is to find a relation between three types of representations of a C-star algebra. Namely, we are going to discuss non-degenerate representations, cyclic representations, and Jns representations.
I'm sorry, in particular, we get that every separable C-star algebra is isomorphic to some subalgebra of bounded operators on a usual little two space. Yes?
Yeah, exactly.
Okay.
HF is separable, so it is isomorphic to a little L2, and H becomes isomorphic to H. A is isomorphic to a closed star subalgebra of B of L2. Yeah. So roughly what we're going to do is to prove the following two facts. The first fact is that each non-degenerate representation of a C-star algebra is isomorphic to a Hilbert direct sum of cyclic representations. And the second fact is cyclic representations and GNS representations are in fact equivalent notions. Okay, so suppose that we have a C-star algebra A. And suppose that H is a star module over A. We denote by AH the linear span of all elements of the form AX, where A runs over A and little x runs over H. So clearly this is a submodule of H. And we say that H is essential if this submodule is dense in H. H is essential, or another name is non-degenerate, if the closure of H, the closure of AH equals H. And of course, the same terminology applies to representations. Traditionally, when we speak about representations, we use the word non-degenerate, and when we speak about modules, we say essential. But these are equivalent notions, equivalent names for the same notion. In the general case, the closure of this submodule is called the essential part of H, and it will be denoted by H essential. Okay, we have the following simple result, proposition. The essential part of H is indeed a closed essential submodule of H. is a closed essential submodule of H. And moreover, if we look at the orthogonal complement, then A acts on the orthogonal complement trivially. The action of A on the orthogonal complement of the essential submodule is trivial in the sense that AX is 0 for all A in our algebra and for all X in the orthogonal complement of the essential submodule. Of course, it's clear that the essential submodule is indeed a closed submodule just by construction. So AH is a submodule, and the closure of a submodule is a submodule. So it's a closed submodule. Now, why is it essential? Well, we know that A has an approximate identity. It's essential here. A is a sister algebra, so A has an approximate identity. And this implies that we have the following equality. A is the closure of A squared. That is the closure of the linear span of all elements, all products A, B, where A and B run over A. So this equality is immediate from the fact that A has an approximate identity. Okay, now if we take the essential submodule and if we calculate the following submodule of the essential submodule, so we want to prove that this is actually the whole essential submodule. So what is this? Well, by definition, this is the following. Yeah. So now, for continuity reasons, I can remove one of the lines here. And for the same reason, I can put another line over A multiplied by A. But since the closure of the A squared is A, this can be written in the following way. But this is nothing but the essential submodule. And we see that the essential submodule, the essential part of A is indeed an essential submodule. Okay, finally we have to show that the action of A on the orthogonal complement is trivial. Well, so we take an element in the algebra and an element X in the orthogonal complement of the essential submodule. And we calculate the inner product of AX by itself. So what is this? This is X by A star AX. But now the definition of the essential submodule implies that this element sits in the essential submodule. And since X is orthogonal to the essential submodule, this is 0. So this implies that AX is 0. And this completes the proof. So as a result, we see that each star module over A is decomposed as the Hilbert direct sum of two summands. The first summand is essential, and the second summand is trivial. This is convenient because this trick enables us to reduce many facts on arbitrary star modules to the case of essential star modules. Okay, now let's introduce cyclic star modules. the definition is as follows. The cyclic submodule of H generated by an element little x is the following submodule. We denote it by AX. So this is the closure of all elements of the form AX, where A runs over our algebra. So again, it's clear from this formula that this is a closed submodule of H. In general, I don't claim that the cyclic submodule generated by X contains X. In general, this is not true, but this is true provided that little x sits in the essential part of H. If X, now this is true, but before we prove this, we'll need another property of essential modules, which is also quite convenient. So let's prove this result. So we have the following proposition. Suppose that A is a C-star algebra as before, and suppose that E lambda is an approximate identity in A. And suppose that H is a star module over A. I claim that the essential part of H consists precisely of those elements X in H for which X is the limit of E lambda X. So this is an equivalent characterization of the essential part. To prove this result, we need a simple but useful lemma, which is fairly standard, a lemma from functional analysis. Suppose that we have two Banach spaces, E and F. Banach spaces. And suppose that T lambda is a bounded net of bounded linear operators from E to F. And suppose that M is a total subset of E. Total means that the linear span of M is dense in E. And also let's suppose that for each element little x in M, the following net T lambda x converges to some element of the space F. I claim that in this case, there exists a bounded linear operator T from E to F such that T lambda converges to T pointwise. that is for each x in E, T lambda of x converges to T of x. In other words, if we have a pointwise convergence of a bounded net over a total subset, then the same net converges everywhere to a bounded linear operator. The proof is a standard exercise in functional analysis. Okay, let's now apply this lemma. So we want to prove this proposition. We want to show that the essential part of our module H consists precisely of those vectors for which this equality is satisfied. Well, the one-way inclusion is clear. Clearly, the right-hand side is contained in the left-hand side. So if x is equal to this limit, then of course it is in the essential part. And to prove the opposite inclusion, we observe that this equality holds for each element x of the form ay, where a is an a and y is an element in our module. I'll just substitute ay here, and since e lambda a converges to a, we see that this formula holds. And now by the definition of the essential part, the set of all such products ay is total in the essential part. And so the above lemma implies that the same equality holds for each element in the essential part. The same holds for each element x in the essential part of H. And this completes the proof. Okay. Okay, let's now come back to the definition of a cyclic submodule. So I claim that if our element x is in the essential part, then it belongs to the cyclic submodule. So this is a corollary, actually, of the above proposition. If little x sits in the essential submodule, then it belongs to the cyclic submodule generated by x. Well, indeed, to prove this result, we just use the formula from the previous proposition. So x is equal to the following limit, and this limit obviously belongs to the cyclic submodule generated by x. And that's it. Okay, so now our next goal is to show that each non-degenerate star module over A is isomorphic to the Hilbert direct sum of a certain family of cyclic submodules. Let's start with the following simple exercise, which shows that if we have a family of pairwise orthogonal closed submodules of a fixed star module H, then the notion of their Hilbert direct sum is essentially equivalent to the closure of their algebraic sum. So suppose that H is a star module over A, where A can be an arbitrary Banach star algebra. And suppose that HI is a family of closed submodules, closed pairwise orthogonal submodules. Then there exists unitary isomorphism. Unitary isomorphism of A modules between the Hilbert direct sum of this family and the closure of their algebraic direct sum within H which takes each element in the Hilbert direct sum, that is a square summable family, xi, to their sum. So in particular, I claim that this family is summable, and this correspondence is a unitary isomorphism of A modules. This is quite easy, just a standard exercise in functional analysis. So in this case, if the direct sum of HI is dense in H, then in this case, we say that H is the Hilbert direct sum of the family HI. Well, formally, it is not the same because the Hilbert direct sum consists of square summable families, but it is isomorphic, canonically isomorphic by the above observation. And so we can, this is slight abuse of terminology, but we say that H is the Hilbert direct sum of the family HI. Okay, now we have the following result. Proposition. Suppose that A is a C-star algebra. Well, maybe let's better call it a theorem because of its importance. Suppose that A is a C-star algebra and H is a non-degenerate star module over A. I claim that there exists a family HI of closed pairwise orthogonal submodules, closed pairwise orthogonal cyclic submodules of H such that H is their Hilbert direct sum in the sense of the above convention. So actually, this means that their algebraic direct sum is dense in H. The proof is a standard application of Zorn's lemma. We denote by M the set whose elements are families of closed pairs orthogonal cyclic submodules. Pairs orthogonal non-zero cyclic submodules of H. So this is a set. This set has a natural order relation, just the inclusion. It's a simple observation that this set, this ordered set, satisfies the condition of Zorn's lemma. This is very easy. If you have a chain in M that is a linearly ordered subset of such families, then you can just take the union of all families in this chain, and the resulting family will be bigger than any element, any family in this chain. Okay, so by Zorn's lemma, this set has a maximal element. So let HI, so this is a family, and this family is maximal element. Let it be maximal element of M. And let H0 denote the closure of the algebraic direct sum. Well, by the orthogonal complement theorem, we have the following decomposition. H is H0 plus H0 orthogonal. And I want to show that the orthogonal complement is zero, is trivial. Well, indeed, suppose that this is not the case. So suppose the orthogonal complement is not zero. And let's take any non-zero element in the orthogonal complement. And let's do the following. Let's take our maximal family, HI, and we add only one element to this family, namely the cyclic submodule generated by X. So I claim that this resulting family is still an element of M. Well, indeed, X sits in the orthogonal complement of H0. We know that the orthogonal complement of a submodule is also a submodule. And so this is contained in the orthogonal complement. And so this cyclic submodule is orthogonal to each of the submodules HA. So this bigger family is also a family of pairwise orthogonal cyclic submodules. And also this cyclic submodule is non-zero because it contains little x. And it contains little x because our initial module is assumed to be essential. So this family sits in M, and obviously it is strictly bigger than HI. And this is a contradiction. Because, our family HI is assumed to be maximal. So this contradiction shows that the orthogonal complement is trivial. And so H becomes the Hilbert direct sum of the family HI. Okay, so now let's find a relation between cyclic representations and Jns representation. Oh, I have only 5 minutes left. It seems that this is not enough for me. Well, in this case, that's all for today. And at the beginning of the next lecture, our first goal will be to show that cyclic star representations and GNS representations of a C-star algebra are actually equivalent notions. So each GNS representation is cyclic, and on the other hand, each cyclic representation is unitarily equivalent to a suitable GNS representation. And in fact, this correspondence becomes a bijection between the set of positive functionals and the collection of all cyclic representations equipped with fixed cyclic vectors. So this will be our next goal for the next lecture. And after we prove this, we begin to discuss tensor products of C-star algebras, which is a vast and interesting subject. And we will need tensor products to define compact quantum groups. Okay, so that's all for today. Thank you.